Hello, in today's video we're going to be talking about quantum numbers. We're going to be moving away from this idea of the orbit, which we saw in Bohr's model of the hydrogen atom. Remember, Bohr's model had the nucleus, it had concentric circles circling around it, and the electrons moved in these circular orbits. We know this to not be true. At the beginning of the semester we talked about that our new understanding of electrons is that they're kind of smeared out all over the place. So there's some probability of the electron being somewhere near the nucleus, but not in a circular orbit. So it can be found almost anywhere within these rings as well. So we're going to move away from the Bohr model of the hydrogen atom, and we're going to be moving into quantum mechanics. Now, quantum mechanics deals with probability. And since we know that I can't draw, it's going to be easier if I talk about the probability information tomorrow in class. So I'm just going to focus on the quantum numbers that we'll be using in this video. And then we'll learn more about the probability, about what equations we use to solve for these. It's known as the Schrödinger equation. This is how we solve for electrons in the quantum world. But for right now, I just want to talk about the three different quantum numbers that we're going to be using for this part of the class. We'll add in the fourth quantum number in the next chapter. So the first quantum number I want to talk about has the symbol of n, lowercase n. This becomes difficult because n is generally reserved for moles. But when talking about quantum numbers, n refers to the principal quantum number. Principal quantum number. So what this is, this tells you the size of no longer the orbit, but the orbital. Size of the orbital. So we knew the Bohr model had these concentric circles. Really what happens is the electron can be found everywhere within these rings if it's the first quantum number, which means we're going to have, instead of a circle, we're going to have, I'm trying to draw a three-dimensional sphere. This is going to be a sphere where the electron can kind of be everywhere. Okay. So we're moving away from the orbit, the classical Newtonian physics, to the quantum world where the electrons can be everywhere and everything is dealt with probability. So we're moving into this thing called an orbital. Okay, great. So what values can n take? N can take any whole number positive integer value. So n can be 1, 2, 3, ... all the way up to infinity. Really, really big. So what does that mean? That means that our initial principal quantum number, if n equals 1, and let's say we're in the s orbital, which we'll figure out what that is. We have our electron looking this. This is going to be our smallest shell. If we go up to the n equals 2, this is going to be a larger shell. Still, electron can be found everywhere. N equals 3, it's still going to be even larger. So the size of the orbital increases with an increasing n number. This is called the principal quantum number. It can range anywhere from 1 to positive infinity, and tells you the size of the orbital. So that's the first one that we're going to talk about, the first first quantum number that we're going to be talking about. So just remember, n tells you the size. It's also related to the period number on the periodic table. As you move down the periodic table, you increase your principal quantum number. So we'll be talking about this, adding electrons in, taking electrons out. That's what we're going to start doing for basically the rest of the semester. So we have n. Our second quantum number has a connotation of L, denotation of L, and this is called the angular momentum quantum number. Angular momentum quantum number. And this is related to n in a very specific way. L can take any value from 0, 1, whole number integers, all the way up to n minus 1. So how would this work? If n is 2, L can take any value starting at 0 and moving up in whole number increments until n minus 1. In this case, n minus 1 would be 1. So we only have two values for L here. We have a 0 and we have a 1. If n was equal to 3, L could take 0, 1, or 2. So as you can see, it goes up in increments, and it can only go up to n minus 1 of the value. So what does the L, the angular momentum quantum number, tell us? Well, it's the shape of the orbital. So this is the shape. If L equals 0, we have our sphere. We also denote this as an s orbital. If L equals 1, we denote that as a p, and we get this dumbbell shape. The electrons can be in either lobe. L equals 2, this is called your d orbital. We have a bilobal distribution, kind of looks like a clover, four-leaf clover. And we have, this is called the d orbital. L can keep going up, L equals 3, this is your f orbital. I can't draw the f orbital, your textbook has a good picture of it, but these are generally the three different shapes of the orbitals that I will have you guys draw for the rest of the semester. So the principal quantum number tells you the size, the angular momentum quantum number tells you the shape of the orbital. Great, so L equals 0 is the s orbital, L equals 1 is the p orbital, L equals 2 is the d orbital, and so on. Okay, so now we're going to get to our last quantum number. This is going to be called our magnetic quantum number. It's denoted as sub L. This is the magnetic quantum number. It takes values from minus L all the way up through 0, all the way up through positive L, okay, in whole number increments. So let's say n is equal to 3. We know that L can be equal to 0, 1, or 2. Let's take this L equals 2 value. So our m sub L, each of the m sub L's will be related to a specific L value. So this is going to be m sub L, and that's going to be of the 2, where L equals 2. We can range from -2, -1, 0, +1, +2. If we were to take the L equals 1, so m sub L equals 1, we would range from -1, 0, to +1. And if m sub L equals, the L equals 0, we would just get a 0 value. So you can see that we're going to have a lot of different m sub L's. Now what is m sub L? It is actually the orientation of the orbital. Orientation of the orbital. So n is the size, principal quantum number, L is the angular momentum, m sub L is the magnetic quantum number, and it's the orientation. So let's take m sub L equaling -1, 0, and 1. This, well, let's start up higher. Let's say we're taking n equals 3, L equals 1, and we're taking this value here. So we know that L equaling 1 means that we're in the p orbital, which means we're going to have a look that looks something like this, an orbital that looks like that. Now, each of these m sub L's is assigned a different orientation in three-dimensional space. So we have -1, 0, +1. This last one's supposed to be a little bit bent, so it's in between, like that. So it's bent over on this side a little bit. But each of the m sub L's is related to a different orientation in space. So if we look at the m sub L equals 2, we're going to have 5 different orientations of the d orbital. M sub L equals 0, we're going to have 1 orientation of that. And with that, I want to cut this video short, and I want to say this is what we're going to be talking about tomorrow in class. And have a great night. I will see you all tomorrow. So we have these 3 different quantum numbers, n, L, and m sub L: size, shape, and orientation, principal quantum number, angular momentum, and magnetic quantum number. Have a great night.